Hmm? Good. As usual. Okay. So let us continue with the yes block elements. Yes block elements. As we have seen in the periodic classification of elements, in the modern periodic table, the elements are classified into 4 blocks. The S block elements on the left extreme of the periodic table. The P block elements on the right side of the periodic table. The D block elements between the S and the P block elements. And the F block elements, the 2 rows below the main table. So there are 4 blocks of elements in the modern periodic table. Now let us see the S block elements. What are the specialities of the S block elements? You know, S block elements are the elements of a group 1 and group 2. These are the elements of a group 1 and 2. Group 1 and 2. These are the S block elements. Group 1 and group 2. And these 2 groups are on the left side of the modern periodic table. In the S block elements, if you write the electronic configuration, can see that the last electron enters S level in the outermost shell. The last electron enters S level of the outermost shell. When we write the electronic configuration, the last electron enters S level. For example, you take a group 1 elements. Say, for example, lithium. Group 1, lithium. We know atomic number is equal to 3. And the electronic configuration will be, there will be 3 electrons. And the configuration will be 1s2, then 2s1. See here, the last electron enters the S level. Similarly, you take a group 2 elements. For example, you take beryllium. Beryllium, atomic number 4, beryllium. Write the electronic configuration. That is a 1s2, then 2s2. See, here also the last electron enters the S level. Last electron enters the S level. Now you come to the inner core. For example, you take lithium. The inner core of lithium is 1s2. 1s2 is the electronic configuration of the nearest noble gas, helium. 1s2, that is the configuration of a helium. So helium, then 2s1. Helium 2s1. Okay. Similarly, you take beryllium. 1s2, 2s2. The inner core, 1s2. That is the electronic configuration of the nearest noble gas, namely helium itself. Helium and 2s2. So what is there in the inner core? In the inner core, there is the noble gas configuration. In the inner core, there is noble gas configuration. In this case, the noble gas is helium, maybe neon, argon, etc. So there will be the inner core of a noble gas. So we can write the general electronic configuration like this. The general electronic configuration will be like this. That is the inner core of a noble gas. Inner core of a noble gas. And the outer level will be NS1, NS2. So NS1 to 2, NS1 to 2. That is the general electronic configuration of the S block elements. There is the inner core of a noble gas. And the outer electronic configuration will be NS1 to 2. Say, for example, group 1, NS1, and group 2, NS2, NS2, outermost level. So in general, the S block elements have the electronic configuration as noble gas configuration, then NS1 to 2, NS1 or NS2. NS1, that is for group 1, and NS2, that is for group 2. So in the S block elements, while we write the electronic configuration, the last electron enters S level. Last electron enters the S level. The S level is the valence level. The valence level is the S level. And these are the elements of group 1 and group 2. Group 1 and group 2. In group 1, there is a NS1 configuration in the outermost level. And group 2, there is a NS2 in the outermost level. So in general, the S block elements, all these are metals, the S block elements can have the general electronic configuration as a noble gas core and NS1 to 2, NS1 or NS2. Now let us see group 1 and group 2 separately. Let us see group 1 and group 2 separately. Do you know group 1 elements? Group 1 elements. You know what is group 1? Group 1. Group 1 elements are called alkali metals. Alkali metals. These are the alkali metals. Do you know which are the elements in group 1? Which are the elements? In group 1, that is alkali metals, the elements are, which are the elements? The elements are lithium, sodium, potassium, rubidium, cesium, and francium. So these are the elements in group 1 or alkali metals. Lithium, sodium, potassium, rubidium, cesium, and francium. These are the elements in group 1. They are known as alkali metals because they can form alkali, the hydroxide. Lithium can form lithium hydroxide. Sodium can form sodium hydroxide. Potassium can form potassium hydroxide, KOH, etc. And these are alkalis. These are bases. And the soluble bases, hydroxides, are alkalis. They are alkalis. So they can form alkali, and therefore these elements are called alkali metals. So alkali metals are group 1. They are lithium, sodium, potassium, rubidium, cesium, and francium. Among these, francium is a radioactive element. This is a radioactive element. Not only radioactive, it is a missing element also. That is a radioactive element. It is a missing element. Now, let us say the general electronic configuration of a group 1 or a alkali metals. What will be the general electronic configuration? Electronic, electronic configuration. The general electronic configuration that is equal to, there is the noble gas inner core, noble gas inner core, and then NS1. There is one electron in the outermost shell. In the valence shell, there is one electron. So a number of valence electrons that is equal to 1. Number of valence electrons that's equal to 1. We can take two examples to illustrate this. Say you take a lithium, atomic number 3, and the configuration is 1s2 to s1. That is equal to, what is 1s2? 1s2 is the configuration of the noble gas helium. So helium configuration and 2s1. 2s1. Now you take the next one, sodium. Sodium, atomic number 11. And the configuration is 1s2, 2s2, 2p6, then 3s1. 3s1. That is the configuration. So in the outermost level, there is one electron in the s level. In the s level. And what about 1s2, 2s2, 2p6? 1s2, 2s2, 2p6. How many electrons are there? Totally 6 plus 2 plus 2, 10 electrons. 10 electrons. And the configuration 1s2, 2s2, 2p6, configuration of 10 electrons, that's of neon. The noble gas neon, atomic number 10, neon. Then 3s1, 3s1. See here, the inner core is of the nearest noble gas. Similarly, you take potassium. Potassium, the inner core will be of argon. Argon, 18, atomic number 18. Potassium is 19. So there will be 18 argon and 4 S1. So in general, the alkali metals or group 1 metals have the general electronic configuration as noble gas inner core with a NS1, NS1, where NS is the outermost level or the valence level. In the valence level, there is only one electron. Okay. Now let us think of the metallic character of these metals. All these are metals, I told you, alkali metals. And since these are metals, these are highly electropositive. These are electropositive. All these are electropositive. What is meant by electropositivity or metallic character? What's meant by electropositivity or metallic character? That is the tendency of an atom to lose electron. Tendency of an atom to lose electron to form a cation, a positive ion. That tendency is called electropositivity or electropositive character or metallic character. We have seen that metals have a tendency to lose electron. All the metals have a tendency to lose electron with the formation of a positive ion or cation. If one electron is lost, then a plus one ion is formed. Unipositive ion is formed. If two electrons are removed, plus two ion, dipositive ion is formed. Now you come to the alkali metals. You know, Alkali metals are these are the largest atoms in a given period. In a given, you have studied that in the periodic classification. In the periodic classification, you have studied that. That the left extreme, there is the largest atom. And the right extreme, there is the smallest atom, except the noble gases. Noble gases. You consider only up to, say, group 17 halogens, up to halogens. You just forget about the noble gases. They are having slightly larger size. But from left to right in general, the atomic size decreases. Atomic size decreases. So at the left extreme of the period, there will be the largest atom. And alkali metals are at the left extreme of each period. And so these are the largest atoms in each period. These are the largest atoms in each period. And therefore, they have, say, a high tendency to lose electron. These are very large atoms. And the outermost electron, that is the ns1 electron, the outermost electron is loosely bound. It is loosely bound to the nucleus. And therefore, the electron can be easily removed. So the loosely held valence electron can be easily removed, forming a unipositive ion. Unipositive, unipositive ion. The loosely bound valence electron, outermost electron, can be easily removed because the atom is the largest one in a period. In a period, alkali metal atom is the largest atom. And so the outermost electron is loosely held. And therefore, the outermost electron or the valence electron can be easily removed. And therefore, they can form unipositive ion. There is only one electron in the outermost level. There is only one electron in the valence shell. And that valence electron, single electron, can be easily removed, forming unipositive ion. Say, for example, lithium gives Li plus ion, sodium gives Li plus Na plus ion, potassium gives K plus ion, etc. And so, alkali metals are highly electropositive. They are highly electropositive. They are mostly electropositive. They are mostly metallic in nature. They have the highest metallic property. Metallic property is the same as the tendency to lose electron. The tendency to lose electron forming positive ion. That is metallic character. So alkali metals are the most metallic elements in the periodic table. Now you think of the tendency to lose electron from top to bottom. From top to bottom, what will be the tendency to lose electron? You know, from top to bottom, what happens to the atomic size? From top to bottom, what happens to the atomic size? Say lithium, then sodium, there are three, then potassium, say 1, 2, 3, 4 cells. Say down the group, what happens? From top to bottom, from top to bottom, the atomic size increases. In a group, from top to bottom, atomic size increases. Atomic radius increases. Atomic size increases. Since atomic size increases from top to bottom, the metallic character increases. The metallic, metallic character, metallic character, uh, character, the metallic character increases from top to bottom. The electropositive character or electropositivity, electropositivity, electropositive character or electropositivity increases from top to bottom. The electropositive character or electropositivity or metallic character increases from top to bottom. What the reason? That is because down the group from top to bottom, the atomic size increases and the electrons are loosely held. The attraction between the outermost electron and the nucleus decreases. So down the group, the atomic size increases and metallic character increases, electropositivity increases. Do you know what's the reason for the increase in the atomic size? I told you from top to bottom, the atomic size increases. The atomic radius increases. Why? What's the reason? From top to bottom, there is a opening of new shells. See here, there is a opening of a new shells. And due to the opening of new shells are added. Down the group, new shells are added. And therefore, down the group, from top to bottom, the atomic size increases. If it is so, you take, say, lithium, sodium, potassium, rubidium, cesium, and francium. You just say, forget about francium, that is radioactive, missing element. So you consider the remaining elements, lithium, sodium, potassium, rubidium, and cesium. If it is so, cesium is the largest element. That is the largest element. Among the stable, non-radioactive elements, cesium is the largest element. And it is the most, the metallic element. Okay. Now let us see a property known as a diagonal relationship. We know the first member in this group, first member in the alkali metals, the first member is lithium. Lithium. Say lithium, sodium, potassium, rubidium, and cesium. Okay. Now you consider the next period. This is group one. This is a group one, and this is a group two. Group two. Say you take these two groups. These two groups you take. Lithium. Say after lithium, there is beryllium in group two. Then after sodium, there is a magnesium in group two. Now you can see that the properties of lithium are similar to the properties of magnesium. Magnesium. The properties of lithium are similar to the properties of magnesium. Say magnesium is a member of group 2. Group 2. While lithium is a member of a group 1. But the group 1 member lithium shows similarity with the group 2 element magnesium. Here, lithium and magnesium are diagonally situated. They are diagonally placed, diagonally situated elements. And this similarity in the properties of the diagonally situated elements, that's called a diagonal relationship. Diagonal, diagonal relationship. Relationship. So the similarity in properties between the diagonally placed elements, diagonally situated elements, that's called a diagonal relationship. So here lithium shows diagonal relationship with magnesium. Lithium shows diagonal relationship with magnesium, and that is due to the similarity in size as well as charge by radius ratio. Charge by radius ratio. Among these, say sodium and potassium, these two metals are biologically important metals. Biologically important metals. You know, sodium ions, Na plus ions and K plus ions, they play a very important role in our biological system, in our, say, cell fluid system, to maintain the cellular pressure, the body pressure. See, these ions, sodium and potassium ions, they perform very important role. So Na plus and K plus ions are biologically important ions. So sodium and potassium are biologically important elements. They perform very important, very important biological functions, especially to maintain the pressure, blood pressure, BP. You know, if the amount of Na plus is increased, BP increases. If the amount of Na plus is decreased, BP, blood pressure decreases. You know, so they have a very important role in maintaining the body pressure. Okay, so Na plus and K plus ions perform very important biological functions, and they are biologically important ions. Okay, let us see more details in the coming classes. So let me stop now. We can continue in the next class.